what can I say? Okay, so thank you very much, Carlos. It's a pleasure for me to be here after so long. And well, I've visited before for sure, but it's really, really nice to come back here. I actually wanted and hoped to come back to an event that was organized to honor my former supervisor, Juan León. But unfortunately, Juan is not here. He's recovering from surgery at home right now. Seems to be okay. I don't know. I will see him today. But in any case, I told Carlos, I already have the ticket, so I'll come anyways. Maybe I can give a little seminar, you know, like familiar kind of thing. So this kind of familiar seminar is the kind of philosophy that I have for my slides. All right, so this is, the title says here, Engineering Negative Stress Energy with Quantum Energy Teleportation. So quantum energy teleportation is a protocol that is rooted in quantum information theory, but in the context of in the context of quantum fields. It's a relativistic quantum information protocol that was introduced by Professor Masahiro Hota. This is in Hokkyu University in Sendai, in Japan. And what we do, I will talk about this protocol in the context of quantum thermodynamics. And what we do here is use this protocol to try to engineer distributions, like custom-made distributions of negative stress energy density as much as we can in the context of quantum field theory. So this is a work that I did with Nicolas Funay. Nicolas Funay is one of my PhD students in Waterloo. It's published, this is the reference, and I think that with no more, I mean, this is, again, very familiar. Interrupt me is designed so that you can interrupt me. And I apologize in advance for like the crudeness of the slides and so on. It's because, as I said, it's a little bit familiar. Anyway, so motivation. So what do we want here? So in the long term, so we want to generate custom-made distributions of stress energy density to engineer curvature, right? So this is the cartoon I use, which is, this is, by the way, Nicolas Funay, the PhD student I'm talking about. So what we want to do eventually is something like this, right? So be able to prepare states of space-time, of distributions of space-time curvature. And well, of course, we know how to engineer space-times. You just, get a mass and shape it and give it the formula you want. Keep it stable somehow. That's not my problem. That's engineering, right? But we know how to engineer custom-made a little bit space-times, get mass, accelerate masses, things like that. We can all do. Now, it becomes more interesting when you can have negative stress energy densities, because if you were to take general relativity seriously, we will talk more about that and those solutions and stability and all.
So you're going to ignore back reaction.
And in this work, I'm going to ignore back reaction. I'm going to mention things about back reaction, but I'm going to ignore back reaction in this work, yes. Which is like, if we are to take relativity seriously, if we source Einstein equations with a negative stress energy density, look that I have a T, non-expectation of T or anything like that. If we really had negative stress energy density, we are violating, in particular, we violate the weak energy condition. Then Einstein equations tells us that there are solutions that include, that are pretty exotic, solutions that include wormholes, warp drives, or negative gravity if you want, anti-gravity, or whatever you want. Regular matter, so classical matter, if you want, cannot violate negative energy, the weak energy condition. However, we know for a while that quantum fields, on average, can violate the average weak energy condition. So you can have negative densities of stress energy. It cannot be all as negative as you want, given if you have a spatial extension, you cannot make it all the negative that you want. There's some bounds. This is one of the quantum inequalities originally derived by Ford and Fenning. And there are many others that came after that, like Flanagan and other people developed this more to include more general cases of this. But this kind of illustrates the fact that if you actually have a distribution in some region of space-time, then the violation is bounded from below. So you cannot get as negative as you want for a finite region. In principle, you can make the region smaller, and then we will talk a little bit about that, and get higher violations, but there's a price that you have to pay. That's the so-called quantum interest conjecture that we will talk a little bit. But the point here at this point is that quantum fields can violate, on average, if we source Einstein equations with the average stress energy density, and at the end, if you want, we'll talk about fluctuations, but in principle, on average, we can violate this condition.
So tau zero is the size of the region?
That's right. So, how can we engineer these violations? Can we actually generate a protocol in which we can engineer these violations? So before getting into that, let's talk a little bit about quantum energy teleportation in the context of quantum thermodynamics. So this is a slightly different topic, but it's relevant and we will need it, so bear with me until we finish, all right? So let's talk about thermostates. So this is the passivity of thermostates. We know, I mean, classical thermo already, thermostates are passive. What does that mean? I cannot extract work from a thermostat alone. I need two thermostats, for example. With that, I can extract work. We know that from undergrad thermodynamics. Quantum formulation, we can actually, so thermostats, we know, are actually passive. So unitarily passive, which means no unitary operations can have a negative energy cost. So what does that mean? So if I have a thermostat, applying any unitary operation on the thermostat will have a positive average energy cost. You see, this is the expectation of the Hamiltonian before and after performing the operation. Of course, it's assuming if it's a thermostat, if it's a finite dimensional system and so on. If you have a quantum field, you can think of a KM state. So doing unitary operation on a thermostat will never have a negative energy cost on average. Okay? Of course, passivity implies local passivity, local unitarily passivity, right? So local operations, so if you imagine have a many-body system and then you act on one of the components of the system locally, then of course this local unitary is a particular case of any unitary, and therefore you cannot extract energy by locally acting on the system. Okay? If I have the whole table and I act here locally, I'm not going to unitarily, I'm not going to be able to extract any work. Of course, this is just a consequence of the stability of the equilibrium state under unitary perturbations. Anyway, so we talked about unitary operations, but what about if we allow for generic operations, right? If we allow CP-TP maps. So, of course, we know ways of doing that. If we allow any operation, it's easy. You get an ancilla that is cold, put it in contact from the, with the system, maybe locally in contact, as in touching the table here. If the table is very hot and my finger is really cold, I'm going to get a net energy flow towards me. We know that, everyone's been burnt, right? So this is possible. So we know that in general, we can, with a general CP-TP map, we can extract work from a thermostat. Now, the question is, this operation I described, like thermal contact, is a local operation? The answer is no, not really. It's not a local operation. So the experience of getting burnt requires energy flows. And those energy flows actually involve in time evolution the whole system. There's an energy flow, net flow of energy from the whole system to your finger. So the thing that I just described naively is not just a local operation in general. There's a question? No. Okay. So usually non-local.
Excuse me, what is ancilla?
It's a system that, so an ancillary system is an auxiliary system. Something that you use, for example, something called my finger would be that, for example. If the table is hot and I want to extract energy, I can do it by allowing for a flow of energy from the table to my finger. My finger would be the ancillary system that I connected. All right, so the question, can we extract energy purely locally by using a colder ancilla? So again, the ancilla here is the hand, cold hand, that is colder than the system. Think of a system as something really hot. We touch it. The question is, like very fast, we don't allow for energy flows. We just touch it locally. Okay? Will the hand get burnt? So the answer is actually no, not in general. In fact, the hand can get colder. For a very general case, for a very general family of states here, I'm going to talk about what kind of systems would have that property. This is what is called local passivity. If the ground state of the system contains max Rank entanglement, so that happens in general when you have Hamiltonians, such that if you imagine the system as a lattice, you have the free Hamiltonians and the interaction Hamiltonians between the lattice elements. If they don't commute, in general, the most likely option, except for zero measure set, is that you have max Rank entanglement in the ground state. That's the condition you need. If the ground state has max Rank entanglement, if you think of a first neighbor interaction, think of spins and a first neighbor interaction that contains max Rank entanglement. Think of a lattice of harmonic oscillators with first neighbor interactions, XX kind of interaction. That has max Rank entanglement, for example. So if the ground state of the system contains max Rank entanglement, max Rank means that it involves all the Hilbert space. So an entangled state is all the Hilbert space. then there exists a temperature T star larger than 0, for temperatures below that T star is not possible to extract work from the system through any local CPTP map. So what the local passivity theorem tells us that if this is satisfied, if the ground state is max rank entangled, then there is a temperature T star for the system under which you cannot do this thing of touching and getting hotter, your finger getting burnt. Like very fast, a local operation, you will not be able to get burnt.
Questions first. This is pure quantum. Then, classically, this does not happen, right?
I don't know if there's a classical analog to this. Seems quantum to me because it requires the max rank entanglement.
That's what I meant.
But it happens with thermal states even if they don't have entanglement. So I think the key is mutual information. This can be recast very likely in terms of correlations.
Correlation.
It's correlation. So the point is, the necessary and sufficient condition is that the ground state contains max rank entanglement. And then the sufficient condition is that the ground state contains max rank entanglement. If that's true, even thermal states that don't contain any entanglement, usually entanglement decays really fast as you heat it up. And in fact, a thermal state will not have in general a lot of entanglement if the temperature is hot enough. Then it will contain classical correlations for sure. And in most systems, the classical correlations increase with temperature. That's what happens with quantum fields, for example. Entanglement decays, but the classical correlations go up. There is a temperature T star under which you're not going to be able to extract energy locally by just touching very fast. That's it's called strong local passivity. And this is also Masahiro Hotta. These are the words I'm talking about.
My second question is the question, relating what you said. It is very fast. Because that's a question of scales, but if it's very fast, you don't have time for energy to...
No, I'm going to discuss that better. I have prepared extra material, we have time, where I will tell you exactly that, yes, no, if you do it instantaneously, in these kind of cases, you can do it instantaneously, and you can compute the speed of the energy flow, which has to do with the inverse of the coupling strength,
yes.
And you can get energy extraction at arbitrarily small scales, much smaller than that. So yes, no flow, yeah.
Actually, you are thinking of thermal states, right? Otherwise, how can you speak of temperature?
Yeah, I'm thinking of thermal states, yeah.
No, but because you said even for thermal states, what I mean...
What I mean is the ground state is a thermal state that contains entanglement, max rank, as per the theorem, but as you heat it up, the entanglement gets lost. In general... Say again? Indeed, but the ground state is a thermal state. And in particular, that means that for the ground state, it will always be true. And for thermal states may not contain entanglement. In fact, usually, if you have first neighbors, for example, entanglement decays exponentially fast as you heat it up with temperature. And goes to zero in a finite time. Because it starts exponentially, but it hits zero at a finite time. Like that's what happens in a quantum field, for example, as well, in a free scalar field, for example. And even so, even if you don't have entanglement left, because you're not...
What do you mean by the ground state is a thermal state?
Temperature zero thermal state, yes.
But is it a pure state, right?
Yes, the temperature zero thermal state is pure. So the exponential of minus, if you want,
all the energy in the exponential drops off when beta goes to infinity.
That's right.
And the only one that contributes is the zero energy.
Yes.
So you get the ground state.
And the ground state is thermal in all the definitions of thermality. The KMS definition has the complex periodicity, it's definitely a thermal state. Anyway, my point is that as you increase the temperature from absolute zero to a finite temperature, entanglement decays, and this can be done, this T star is not the point when you lose entanglement in the thermal state. It goes beyond that. In fact, for many systems, this T star is infinity. For a chain of spins, they actually prove that this T star is infinity. So you can actually get this. You're not going to be able to extract energy locally for a chain of spins, no matter how hot the chain of spins. Anyway, any more questions about this? Okay.
Well, max rank entanglement, sorry, but I don't know what it is.
Max rank entanglement, so it involves, so if the dimension of your Hilbert space is...
You mentioned Hilbert space.
So do you mean that the reduced density matrix in a sub-region of your system is...
What I mean is that the Schmidt composition has all the terms. That's what I mean. So it covers all the terms, all the bases. Okay. Now, what we see, and so this is a kind of graphical representation of what I just said. If you do a very short interaction locally, if you just touch this locally, then what you get is that your hand gets colder. You can touch the sun pictorially very, very fast. If you do it very fast, your hand will get colder. Okay? That's the strong local passivity theorem. All right, so can we break from local passivity? So we said local operations do not allow you to extract work interacting locally. But what about if we allow local operations and classical communication? So we allow also the ability to have two parties doing local operations in different parts of the system, and then being able to communicate, to measure, for example, and reveal the outcome of a measurement, or do a POVM and reveal the outcome of the POVM to the other person, and the other person can use it. So if we assess local operation, I'm not going to enter. I have prepared a relatively quick, full example when one shows how that can be done, but I don't plan to include until the end if we have time, or if there's any questions about it. But for now, you're going to have to trust me. If we assess local operations with classical communications, it is definitely possible to extract energy with local operations. Again, hand-wavy way of seeing it. So when you are, imagine the ground state. If you're trying to extract energy locally from the ground state, you're going to get fluctuations for sure. You act locally, so the ground state is a global ground state. If you act locally, sometimes you're going to get energy. Sometimes you're going to be paying energy. And of course, the average is going to be zero. And in fact, the fact that you're doing some operation that is short duration in time is going to cost you some energy. So all in all, what you're going to do is excite the ground state, and it's going to cost you an average energy for sure. But what this is doing is, okay, let's measure the system somewhere else. Then measuring the system, we get information about the spectrum of fluctuations. By transmitting that information, the person knows how to push the system to just catch the right fluctuations if you want. Therefore allowing you to extract energy from the 0-point fluctuations if you want. Of course, again, I have an example with a minimal QET, which is 2 qubits. You can do it already with 2 qubits. And show 2 qubits coupled with a XX coupling. But I will get that at the end if there are questions about it. So anyway, even from the ground state, I mean, you can break local passivity any point that local passivity exists. If you are below this T star, you can prove that with LOCC you can design a protocol based on, again, one person does an operation that is local, does a measurement, or a POVM, it could be. It could couple some other ancillary quantum system and send it to the other person, and the other person uses that system or that information, if it's a projective measurement, to do a local unitary, actually, on the system locally and extract work from it. Okay? So something like this, you insert some energy. So it's not for free. We're not extracting energy from the 0-point fluctuation. The POVM that Alice does on the system far away costs some energy. Then the POVM generates some classical information or some quantum information. It could be that you couple a quantum system and you just pass the quantum system along. Then you throw the quantum system to B, and B does an informed unitary that depends on the outcome of the measurement on A, and extract energy. And of course, EB is always less or equal than EA. So that's what is called quantum energy teleportation, as opposed to quantum energy extraction or something like that. You cannot extract just 0-point energy because you need first. So the key point is that the energy inserted in A does not travel. You can actually map the energy density in the system, and the energy density on A, you can send this information faster than the propagation of the energy density. Don't think of fields yet. Think of a solid-state system with a low coupling strength. Then that information can be transported, and you can extract energy, not because the energy on A, it's moved from A to B, it's just because you're literally, when you are interacting with B, you see the local ground state still. The action has not propagated through the system yet through the interaction, and you can extract energy. Okay, questions? Good. So this is kind of intuition that I said. Important, the energy does not travel from A to B. Is information what travels from A to B. And that information allows B to do the right operation to extract energy. Okay, so what you're doing is, I write here entanglement. Probably I should write correlations, because again, it can work with thermal states where there's no entanglement, as long as the ground state has max rank entanglement. So you are unlocking 0-point energy locally, consuming the correlation. Actually, the operation destroys correlations. Okay? All right, so this thing that I told you, I was using to illustrate a many-body system. But what about quantum fields? We can think of quantum fields as the continuum limit of a lattice of harmonic oscillators, for example. Quantum fields has that property. The ground state of a free quantum field is entangled between local parts. So space-like separated regions so the ground state in space-like separated regions of space-time is entangled. So can we do something like this? The answer is yes, Masahiro Hotta. That's actually the original. Quantum energy teleportation was originally introduced in quantum fields. It was exported to many-body systems later on. So in this paper, Masahiro Hota engineers a very particular, you can argue unrealistic interaction, which is Alice couples to the field only to left movers. He wanted to show cleanly that the energy doesn't travel to Bob. And because in a massless field, energy travels at the speed of light, and he was using a massless field, says, okay, let Alice just couple to the left movers. So whatever action Alice does propagates to the left, not to the right. So Alice couples 1 plus 1D, therefore they're the couple, very important, otherwise we couldn't say that. Okay, I was seeing Luis' face, I guess. Okay. And what he does, summary in this paper, is basically Alice does a measurement, a POVM, based on coupling a detector, well, a funny detector that only couples to left movers, but it's something like an unrooted detector, a two-level system that is coupled only to left movers of the field. Then the perturbation propagates to the left. Alice sends information to the right, to Bob. Bob uses the information to do a local operation, and indeed, he can extract energy. And what Masahiro shows the extraction of energy, what I focus on is the fact that we started from the ground state, which means that if you start locally, if you actually plot the energy density here, you're going to end up with a little bulge of negative energy because you're extracting energy from the ground state. Therefore, locally, you're going to get negative energy. Expectation value, understood. Okay? So what we want to do here first is let's do it with a more realistic interaction, and let's not focus on the ability to extract work. Let's see how much we can actually use this protocol, engineer a new protocol whose objective is to do custom-made negative energy distributions and assess how good they are at generating negative energy. How close are we to the bounds, and what can we do with it? This is what the work is about. Okay? So the scenario that we want here is the right one. Here's the Masahiro Hota original one. The one that we want is a realistic coupling. We will discuss the coupling in a minute. And then, the action of Alice generates a perturbation of positive energy that propagates to Bob. Of course, the measurement information can travel at most at the speed of light. So you're going to be able to use it. And in fact, you need to use it soon. The information gets outdated soon, so your ability to actually extract energy goes down if you wait. So we really want to do it like that, and we want to see if we can do something like that. Despite having this positive energy density here, we want to compensate for it and create a negative energy distribution and see what it looks like. Okay, this is our objective. Questions? Okay. So, this is what we're going to focus on. So we want to check the state of the field and the energy density. Of course, we want 3 plus 1D for reasons that I will discuss later. And we want the protocol made concrete, still will be, of course, an in-principle thing, but using models that are considered good models for light-matter interaction. We will discuss in a minute. All right. So let me introduce, if there are any questions, let me introduce the particle detector models that I'm going to use as atoms, if you want. So the physics of particle detectors. In general, a non-relativistic quantum system coupled to a quantum field. Why a non-relativistic system? Because we know how to do projective measurements and everything else very well on atoms, on non-relativistic systems that can be very well approximated by a non-relativistic system. And we want to couple it to a quantum field, and the coupling, we want everything, what is Lorentz invariant, be Lorentz invariant, transition probabilities will be indeed Lorentz invariant. The only thing is that my atom, my detector is a system that is not a field. It's a relativistic system of finite or infinite dimension, but a non-relativistic system. Okay, that would, with a good approximation for atoms, that's the case for most atoms, anyways. All right. So the Hamiltonian I write is this is the unrooted Hamiltonian, which is a monopole moment, which has some spatial smearing coupled to a scalar field. Of course, scalar field, let's pick a massless scalar field, which is this. And the monopole moment, as you see, is a sigma x, if you want, in the interaction picture. Think of a two-level system. So the free Hamiltonian would be something proportional to sigma z. And we have an interaction Hamiltonian that couples sigma x to the field. And it's sigma x, but with a spatial smearing integrated, so the detector sees the field in all the points where the detector lives. So the detector is mirrored and sees the field integrated on every point of the detector. And then some switching function, okay, that controls the strength of the interaction as a function of time. Now this is, Merce will probably recognize this easily, and in fact you may wonder why is there I'm recycling a slide, I'm sorry about that, that was made by Anna Blasco for a different work, but it illustrates really well, it's a really nice one. So you see in the interaction Hamiltonian you have the coupling strength, you have the switching function, and then you have the monopole moment here is a little bit different because I put the monopole moment and the integral. The monopole moment here is just sigma plus e to the I omega tau plus sigma minus c to the minus I omega tau. So I put it together with this smearing and integrate it. This is just a volume element. If you were in an arbitrary space, then that would be an integral over the volume element. And it's kind of particularized for particular trajectories, but fine. Detector's trajectory here is a little bit more complicated. If you had some non-trivial trajectories, such acceleration and stuff like that, then you need to pick a frame in which the detector is rigid and stuff. But we're not going to worry about that. We're going to consider only inertial detectors. And then a smearing function that tells you more or less what the detector is. I'm going to discuss where they come from in atoms. They are functions of the atomic orbitals, as we're going to see. Anyway, so you can argue, okay, this under the Witt model, how good is it? I could tell you that quantum opticians usually use that kind of model, and there's several extra approximations, but instead of that, let's see if it really approximates a light-matter interaction. Okay, so imagine that you have an electron in an atom. In a particular reference frame, this is the way the Hamiltonian looks like, right? The Hamiltonian is the interaction Hamiltonian. This is what is called minimal coupling of the electron to the electromagnetic field. And in particular, you can carry out a multiple approximation, a multiple expansion, and stay only with the dipole approximation. And in the dipole approximation, the leading order term that you get out of doing a dipole approximation here is the dipole Hamiltonian. So the dipole of the atom, the dipole of the electron, coupled to the electric field. Okay? Now, this Hamiltonian, if we reduce it to a finite, we don't need to, but let's do it. It's just a sum that we can carry out now. Let's reduce it to a finite number of levels. Say 2 levels separated by an energy gap omega. Then we can write, this is the generic form of it, just writing the matrix elements in the possible states of your Hilbert space of the atom, spanned by excited and ground state. You may wonder why, this is just because it's in the interaction picture. You may wonder why are there no diagonal elements? If you write it in general, you have diagonal elements. Well, because of parity, E with this in the middle and ground with this in the middle vanishes because of parity. So the only terms that survive are the non-diagonal ones that connect ground with excited. So if we introduce the resolution of the identity in here, we get this expression here. Introducing it, you get deltas that you can integrate all the integrals except for one. So if you, what it results is you have this fx and fx star. This fx is just x. Now node operator is x as in the coordinate x. And excited state, this is the conjugate wave function of the excited state, and this is the conjugate wave function of the ground state. So there is a smearing appearing naturally, and that smearing is related to the wave functions of excited and ground state. Well, I'm following this thing is in a little bit more detail in this paper, in section 2 of that paper, if you're interested in seeing it. And then what let's introduce some time dependence in the coupling. We have to put by hand the coupling strength. And if we do that, okay, what we get is that the electromagnetic Hamiltonian, in the dipole approximation, is just the coupling of this dipole moment defined. The dipole moment operator is defined as E, the smearing, sigma plus, the conjugate of the smearing. You see, if the smearing were real, then you can factor it out and looks a lot like the smear monopole moment. Okay, only that this F is a vector, that's why it's bold-faced. It's a vector, has an X as well in it. Of course, a vector coupling, not a scalar coupling, not a monopole coupling. So you get the dipole operator with this mirroring, right? And if we compare the two models, we see that they look a lot alike. Like looking at the Hamiltonian, this is the scalar version of this. So of course, I chose the smearing to be real, but it could be imaginary as well, no problem. I can put an F here, an F star there, no problem. And I can actually use, in fact, it's going to be real for the orbitals. If you want to model transitions, atomic transitions with this, at transitions that have zero exchange of angular momentum, so 1s to 2s, that, for example, would be one of those, and the wave functions are real in that case, so of course that makes sense that it's always real. There's no exchange of angular momentum. You don't need to make it complex in that case. And as you see, this is just what I'm calling here is that if you are studying just 2 levels and you don't care too much about what happens with angular momentum, you can just look at the scalar version, and it's not difficult to generalize results obtained with this in the scalar version to the electromagnetic case. In fact, there's a couple of papers that we've done that actually do write known results such as entanglement harvesting derived usually with a scalar field with full atoms coupled dielectrically to the electromagnetic field with the proper wave functions. I'm hoping that that's not 5 minutes, right? Oh, okay, sorry. All right. So, my claim, and this is a claim, is that the under the Witt detector capture fundamental features of the light-matter interactions when exchange of angular momentum is not relevant. Okay? So this is to justify that the model I'm going to use, which is this one for this work, is rooted and captures the fundamental features of the light-matter interaction. More questions, or questions of any kind? Okay, so now let's get back to what the thing that we want to do. Of course, let's begin with something simpler. Before moving to the 3+1 decays, let's do a toy model first, which is 1+1D, because it's much easier and things are much more clear, and then we'll move to the 3+1 decays. So imagine that we consider the system initially in a separable state. So we have the cubic state A0 and the vacuum state of the field. Again, massless free massless scalar field in 1+1D. And then we have Alice interacting very short. They have a very short interaction. This is a delta. Dirac delta is a kink kind of interaction. Why do we do that? We do that in order to be able to do non-perturbative calculations. This is non-perturbative, so we're not using perturbation theory. And using a delta switching allows us to do it non-perturbatively. You can think of it as the limit of a very short switching, in which the amount of energy that it costs you keep it constant, but then you make it shorter and shorter. Okay, so Alice interacts via this Hamiltonian, first couple sigma x, such an under the width kind of Hamiltonian, and Bob's actually interacts with a derivative coupling. This is just for simplicity of the calculations. It's like Alice couples to phi, Bob's couples to pi, but phi and pi in a freely evolving field is a matter of weighting. One becomes the other continuously, so it's not really a different coupling. This is just prescribing the phases of the coupling, if you want. Okay? Anyway, the system is initially in that state, and then after doing the protocol that I mentioned, is Alice interacts with this Hamiltonian. Then Alice teleports the qubit to Bob. So Alice uses a qubit, couples it to the field through the under-the-width model, and then sends the qubit to Bob. Think of a regular teleportation, regular quantum teleportation, or physically sending the qubit, all right? But this quantum teleportation can be done at the speed of light, that's why. So you do a quantum teleportation to Bob. Bob has the qubit, and then Bob couples the same qubit with this other Hamiltonian where Bob is. Okay, so it's the information travels in the state of the qubit. It's the same qubit. This is, if you want, LOQC, variant of QET. So instead of classical communication, we do quantum communication, as in physically sending the qubit to Bob, or teleporting the qubit. Okay? Then, after doing those steps, first Alice couples to the field, then sends the qubit to Bob, and Bob couples to the field as prescribed. Then the resulting stress energy density, well, renormalized stress energy density, the 0-0 component in the common reference frame of Alice and Bob, because they're not moving. They're co-moving, they're inertial and co-moving. You have several terms that you can identify. One is Alice's positive energy contribution. This is positive. Bob's positive energy contribution. And then you have a right-moving QET term and a left-moving QET term. I call them QET terms because these ones are the ones that can be negative. For them to be negative, you have to play with the state of the qubit. You see this is a function of the expectation of sigma y on the state of the qubit. So if you pick the qubit in the right initial state, you can make this negative. Now the question is, will the negative bits here overcome the positive ones? All right, we can plot them. So if we plot them, this is going to be several steps. So I'm going to plot like in time slices if you want. So this is right after Alice does Alice measurement. Alice is using here a Lorentzian coupling, and that's why, because this goes with the derivative. If you remember, there was a lambda prime here, which is the derivative of Alice's mirroring. Because it goes with the derivative, you had the inflection points in there. So this is the energy, the stress energy distribution after Alice couples to the field. Of course, is the ground state, so the average expectation of the stress energy density grows. The energy density grows. The expectation of the energy density grows when Alice does that. Of course, Alice just modifies the ground state to be an excited state by her action. And then we let it evolve. The perturbation, if you notice, the scale goes to half because this is not the two left moving and right moving parts. This is the whole thing, and the whole thing now divides in two, one right mover and one left mover. And as you see, the half of the energy goes, you see the scale, right? The scale is going to half. It's just rescaling. It should be half the height. One goes to right, one goes to left, and keeps propagating. And at some point, it reaches Bob. Now, here's where Bob is. Alice's positive energy wave packet reaches Bob, and also the information that is sent through a channel, say teleportation, different field or something like that, or a very infrared photon, whatever you want, or physically sending the qubit very fast. The information from Alice's measurement reaches Bob at the same time that the energy pulse generated by Alice coupling reaches Bob. Then Bob couples to the field now using the prescription, and this is what happens. So it doesn't look like a lot because What Bob has done now is put a lot of energy where he was, right? The switching on his detector there is again going to increase. Remember, there's a positive part, increase the energy. But let's wait for the positive energy to propagate both ways, and this is what happens. If it propagates both ways, you have a positive energy contribution that goes left, and a positive and negative energy distribution that travels right. This thing is going to move right. So if you zoom in on that, you see that you get an energy density that is positive, but is overcome by negative energy component in it. Okay, by using this recipe. So Bob has used a quantum energy teleportation recipe, has extracted energy. The field didn't look like the local vacuum, as in the Masahiro original case. It looked like a pulse of energy that Alice sent, and still it's able to overcome it. Of course, with some positive energy surrounded it. Questions? Okay. So now that we've done 1 plus 1D, that is relatively easy, let's do the 3 plus 1D case. Now, the 3 plus 1D case is complicated, but we need it. Because if we want in the long term to talk about back reaction of any kind, and what kind of space-time you can generate with these kinds of distributions and so on, you need dimensions. 1 plus 1 dimensions, there's no gravity. So let's go to the first non-trivial case where you have gravity, which happens to be the one that seems to reproduce experiments too. Let's go to 3 plus 1D. Then there are several complications. To begin with, one single Alice won't do it. That's ridiculous. A single point is not going to do it. We need a distribution of Alice's and a distribution of Bob's, many of them. We cannot tell, so it's not real, but the point being that it's not realistic to consider one atom that has a distribution in space that is huge. Atoms are very small, okay? And if you do it huge, you're going to violate causality anyways too much. So, you need a distribution. Problem, you cannot teleport the state of Alice's detectors to every Bob. No chlorine theorem is going to tell you have a distribution of Bobs, you cannot really teleport your qubit at all. So you cannot use a quantum communication-based protocol. And finally, it's just more complicated, like way more complicated, the math. Okay? So, if we deal with all that, what we do is go in the 3 plus 1D case, what we want is we have Bob's mirroring to be something like that, like in the simplest case, but then you can actually make, one of the things that we prove in the paper is that the results of on the stress energy density, only on the relevant states, the states that maximize quantum energy teleportation, you get the same if you consider a big atom that is smeared on a huge region, or a lot of individual atoms, atomic density, making up a region together. You get exactly the same result. That's one of the longest parts of the paper proving that. It's actually in an appendix, but it's huge, and it's a very important part. Otherwise, we couldn't claim we couldn't do it. So we want to make the smearing of Bob now be composed of individual atoms. And to all of them, we're not going to send quantum information, we're going to send classical information. So Alice is going to, so this is a little circuit showing, I mean, this is well known. You can, an LOQC can be cast in terms of LOCC. Like this, there are two equivalent circuits, so the state for the field. So the state of the field, you can prove that the state of the field gives the same result in both circuits. And the point being that doing the protocol right, what you would do now is Alice's detectors generate classical information. That classical information is sent to every single Bob, the distribution of Bobs, and then every single Bob does the operation. That's the way we're going to do it. Okay. So Alice measures the field by coupling an atom or many atoms to it, measures the non-relativistic atoms, then broadcasts the classical information resulting of the measurement to an agency of Bobs. You can consider a small Alice if you want. But then many Bobs around Alice, for example. We're thinking of a lot of Bobs surrounding Alice. Okay, for example, a sphere of Bobs. Then Bob's agents use that information to prepare atoms and couple to the field. And then what you get if you do that is something that looks a lot like what we had before, only this is a full stress energy density, only quite more different. I mean, I'm just going to show you, but it doesn't make really sense, it's just math. But this is we're going to use later, but it's just more complicated because it's 3 plus 1D. In fact, in the paper, there's a missing phase factor. We need to upload one thing in archive saying that is that doesn't affect the results, but it's a small missing phase factor. Anyway, so what we use here for simplicity is Gaussian smearing functions. So these are the profiles that we picked. These are radial. So the profiles I'll drawn here. So Alice is this small circle here. Bob is this small circle here you want, and then the sections are spherical Gaussians. So the sections are Bob is kind of thin here, and Alice is kind of thick here, next to the center. And this is what the original configuration we're going to use. Okay? Now we do the same business as before with the dynamical picture. So energy density immediately following Alice's interaction. So when Alice interacts, all the energy is put near, it's the same as before, because you use the two inflection points, get the maximum, goes with the derivative, and you get two horns, but it's R, right? And then thing propagates. If we neglect the caustic that you get at R0, of course you get a caustic. It's radial symmetric. If you don't have radial symmetry, you don't get it, but again, that's something irrelevant. So the energy density after the interaction starts propagating. You have a reflected wave, which is the equivalent to the left mover before, and a non-reflected wave, that the ingoing that reflects an outgoing wave. And then propagates to where Bob is, so immediately prior to Bob's interaction. Now Bob interacts, does the thing, does the measurement, the coupling of his detectors after preparing their state based on the measurement, and you see here that there's a region of negative energy density that propagates, surrounded by positive energy density as you go. You see there's a decrease, overall decrease, of course, 3 + 1 dimensions. There's dispersion of both negative and positive energy. And if you zoom in, you see that there's a tiny little bit of negative energy here that remains, that are going to be dispersed as well, wider and shorter, if you want, as it propagates. So it doesn't look very impressive, as is, but there is negative energy. Okay? Okay, now the next step is trying to make it as impressive as possible and see how that compares with the results that we know about how much you can violate quantum inequalities. Oh, sorry, energy conditions. Okay, so going back to the expression, this is the expression we got for the expectation of the renormalized stress energy density. Now, the QET term has this exponential here, that if alpha grows too much, we're going to try to scale the system to see if the scaling is good for us. If we can actually scale it, making it thinner, and see if we can concentrate more negative energy. This exponential factor is going to kill you if alpha increases a lot. So the first rule we need to scale it in a way that is favorable is, okay, no matter what you do to scale it, but alpha better keep the same. Otherwise, you're going to get a problem with this exponential killing you. Okay, so if the smearing of Alice is scaled like this is the scaling we apply. So increasing the coupling strength with this scaling factor and then making it thinner like this, then alpha remains constant. And if additionally we scale the smearing of Bob by increasing the coupling strength like this, n is the dimensions, and making it thinner like that, then the stress energy density scales with sigma n. What does that mean? The total amount of negative energy, using scaling the protocol optimally, it's exactly this kind of scaling. The total amount of negative energy scales with the scale parameter to the dimension -1. This is exactly the optimal scaling that quantum inequality gives for the amount of negative energy that you can violate. And I don't have it here, but you can compare the total amount of negative energy with the total amount of positive energy that is surrounding the area. If you pick an area that is long enough, and then you say, okay, how much positive energy do I have? I mean, if you pick the whole space, you're getting total positive energy, obviously. You've done something to the ground state, total energy is going to be higher. But if you just pick the wave packet that is traveling with this negative energy surrounded by positive energy in a given scale, then you can see how much of negative energy you have compared to positive energy. And this you can compare in the context of the quantum interest conjecture. Many people have worked in that. Ford and Fenning, Matt Visser has worked in that as well, and other people. The quantum interest conjecture tells you, yes, you can generate negative energy densities, and they were working with accelerating mirrors and things like that. But you have to pay a price. You cannot generate negative energy densities alone. Negative energy densities will always be surrounded by positive energy. And the larger you want your negative energy density, the larger the positive energy density has to be. And the larger your negative energy density, the larger the peak of the positive energy has to be. That's what it's called. You have to pay an interest rate. You have to generate more positive energy around it than negative energy. This protocol also saturates the scaling of the quantum interest conjecture, so the amount of positive energy to negative energy grows the smallest possible. The quantum interest conjecture. By the way, it's not a conjecture in 1 + 1D. It's a theorem. And in most cases in 3 + 1D is also a theorem. It's a conjecture in general in dimensions. Okay? Okay, so summary very fast. I don't know how am I doing time-wise. Okay, good. Yeah, I mean, maybe I can even show you QET, which is kind of neat. So QET can be used to operationally generate negative energy distributions. That's so consuming space-like vacuum entanglement. In this case, it's consuming entanglement of the vacuum. and the negative energy packets are accompanied by positive energy packets. So you can generate energy packets that are accompanied by positive energy packets, which is interesting, and the gravitational back reaction. Negative energy packets alone are very unstable, even classically. They tend to be unstable. They disperse fast. If you have positive energy densities around them, then you get confinement. You can get confinement of negative energy density. So it could be interesting in terms of the back reaction. Then the QET protocol scaling saturates the quantum interest conjecture and violates the not this one, not the quantum version. Violates the weak energy condition. This is a mistake. The weak energy condition optimally, as much as it can violate it for a quantum field. So this protocol, if you want a protocol that is in principle constructive and that violates maximally, this is a protocol that does it. So this is kind of the best you can do with a scalar field, okay, on an electromagnetic field. In principle, you can generate almost arbitrary energy density distributions. The shape is just controlled by your distribution of atoms. The cloud that you want to generate mimics, as you saw, the derivative of the smearing. So you get, so the derivative of the smearing for Alice convoluted with the smearing of Bob. So by playing with the shape of how you distribute your atoms, and the coupling strength, by the way, is the density of atoms in here. In this picture in which you have many atoms, this coupling strength can be related to the density of atoms that you have, the sigma scaling of the strength. And playing with the shape with the density of atoms, in principle, you can engineer arbitrary shapes for this negative distribution. Of course, it's going to be surrounded by similar shaped positive energy distributions. And then the energy distributions were close to the limits of the quantum energy conditions. And I think that's pretty much what I want to say. If I have some time and if you want, I can show you quantum energy teleportation if you are interested. I don't know how you feel about it. It's kind of fast, but it's more, let me just show you. Yes, sir. Okay, so just to show you a little bit of how quantum energy teleportation actually works. How can you extract energy from a ground state locally? So consider two qubits A and B and this Hamiltonian. So you have a free Hamiltonian. I added this constant for simplicity. You don't need to add a constant to the Hamiltonians. It's fine. You don't need the F in there. It's just the math is much simpler. You can do it without. So the free Hamiltonians are sigma Z for A and B, and the interaction Hamiltonian is an XX Hamiltonian. The important bit is that it doesn't commute with the free Hamiltonian. Okay? H and K, so you see the coupling strength is K, as you see here, and H and K are positive constants. Okay? Alright, so this is the F actually makes it nicer to have this zero. It doesn't mean much, it just makes things simpler. And also people can say, oh yeah, the local energy densities, not only the total energy is zero, the expectation, if you want to define local energy densities, as in like expectation of HA, expectation of HB in the ground state, and expectation of V, they're all zero. That's what the F does for you, by the way, make it zero. That's not really so important, it's kind of it makes it more impactful, as in like, no, there's no artifact here of non-commuting stuff. Anyway, the ground states you can compute as this form is max rank entanglement, and again, max rank means that it contains the 1, 1 and the 0, 0. If it were three-dimensional, max rank would be 1, 1, 0, 0, 2, 2. Max rank is that involves the whole Hilbert space in the Smith decomposition. Okay? And then we do the protocol. We start from the system in the ground state, G. Alice carries out, in this case, the simplest case, a projective measurement, can be done with a POVM, but let's do a projective measurement, on the observable sigma XA. Repeated many times, this will have an average energy cost that we will call EPA. If we are pumping energy into the system by acting locally on A, of course, it's the ground state, so we are pumping energy into the system. Now, the result of the measurement, which is plus or minus 1, is transmit announced to Bob through the, each bar divided by 2, whatever, 1 plus minus. It's announced to Bob through a classical channel that is supposed to be fast enough, which is faster than the coupling timescale. We will discuss that a little bit later. Okay? With the information of the outcome, the measurement, Bob carries out a local unitary operation that depends on alpha. After many repetitions of this, the average energy cost of this unitary operation will be negative. We'll see. Okay, so basically the idea is you have the ground state. There are two parties. Alice has access locally only to one. There's another one, Bob, far away. They're coupled, though. And then Alice does a projective measurement on her qubit and generates a classical information, a bit of classical information alpha that is sent to Bob, and Bob does an informed unitary UV alpha. Okay, and the claim is that the average energy cost of the local unitary of Bob is below 0. So, first, we do the projective measurement. This is the projective measurement, depending on the outcome that you get, plus or minus 1. This is the projective measurement P alpha that Alice does. So in a single shot measurement, basically you get, after acting on the Alice state, you get the normalized projected state. Okay, you get the ground state and do a projective measurement. And PA is just the expectation of the projector. As usual, this is the usual projective measurement. So, if we repeat this projection on an ensemble of identical setups, we obtain the following post-measurement average state. So we do it many times, and we get the following average density state, density matrix. Now, G had a 0 expectation, so energy expectation, so we can analyze the expectations of rho 1. Now, what happened? What's the energy cost of this first operation? So if we compute it, and you trust me on the math, it's simple math though, we get that the result is that the energy cost of the projective measurement on average, which is the expectation of the Hamiltonians, total Hamiltonian before and after doing the operation, is this F that I had here that is larger than 0. Okay? Alright, classical communication now. So now we send the bit to Bob, and Bob does this informed unitary that depends on the outcome of Alice, which is this one in particular, something that sigma-wise, something that has to non-commute with both the interaction and the free Hamiltonian in this case. All right, so doing that, what you get is that where alpha is the outcome of the projective measurement, and this depends on alpha, so this theta is a function of alpha and the parameters of the system, h, then free energy, and k, the coupling strength. The dependence is this. Okay, the dependence on alpha is just this, and the dependence on the coupling strength is in the angle, is buried in the angle. Now, in a single shot experiment, after doing the projection and the unitary, you get that, and then for an ensemble of many times repeated first projective measurement and the informed unitary, you get that the density state is the density matrix is 2, and if you compute again as before the energy cost of that unitary operation, you do the math, and you get that this is the result. It's difficult to assess if this is positive or negative, but we can do a quick approximation for low values of theta, which is what you get if the coupling strength is small. And then you get that the energy cost of that operation, the average energy cost, is negative. Remember, h and k were positive constants. Okay? All right, so it's a negative energy, so a couple of things. Natural energy flow from A to B. Luis, this answers your question. Is it just the energy flowing from A to B? No, the typical... You see here, without the protocol, of course, the expectation of B is going to increase just out of time evolution without the protocol. So if we actually, the energy expectation of the interaction, here you get, the energy expectation of HB as a function of T, in here if we allow for time evolution, so Alice does the measurement first, projective measurement, inserts energy into the system, that's why it's done first, and then we let free evolution, well, not free, it's interaction with A and B, but evolution with the Hamiltonian H, then of course the expectation of B is going to increase, but you see here that it increases with the inverse of the coupling strength, KT in the cosine in there. Alright? So at time 0 is 0, and it increases with the inverse of the coupling strength. So if the communication happens much faster than that, which in principle you can do it with light and low coupling, then you get that the energy is extracted even before you get a significant contribution from this. Okay, so it's definitely not energy traveling from A to B. And finally, it's like, okay, it's really important to have a POVM. I did it just for fun. Is it really important to have a POVM? If Alice does the projective measurement and Bob does a random unitary without knowing, or the same unitary but not informed, remove the informed part, any unitary, whatever unitary he wants, but removing the informed part, can Bob extract information? So what I did here is that an arbitrary W is done. Okay, that's arbitrary, no information. The only thing is it doesn't depend on alpha. Because it doesn't depend on alpha, factors out of the statistical average of many times on the outcome of the measurement. And because it factors out, you compute the expectation of the Hamiltonian, and then you get the expectation of the Hamiltonian is always larger than 0. So definitely, you need the communication bit. Bob needs to know, needs to be informed, as there has to be, right, in order to extract energy. So this is a very simple model of QET. And with that, I think I'm done. Thank you.
Are there more questions or comments?
Is there any limit in the amount of energy that Alice can teleport for?
Do you mean in this scenario or in the field scenario? So in the field scenario, remember the amount of energy, the total amount of energy because of the scaling can be as big as you want. You can do as much negative energy as you want, paying a price. The price is that it's going to have to be concentrated. The scaling, remember, makes the smearing thinner and more peaked. The integral grows. The total energy, remember, scales with sigma to power n minus 1. So it grows, right? But it's concentrated in less space and is surrounded by more positive energy. That's the price you pay. But that is fundamental. That's the quantum interest conjecture together with Foer and Fenning quantum inequalities. You cannot escape that. It's doing the best you can do for that. Okay? And now you say here, one of the things that I went fast through is that the energy that Bob can extract is always bounded from above by the energy that Alice puts in. So it cannot input too much energy. So there's a limit on how much energy can Alice put in. In a finite dimensional system, it's going to be finite. Alice can do only, the maximally, he can go from the ground state to the highest excited state of the Hamiltonian, right? And by local operations, you cannot, in general, you're not going to be able to approximate that to the best approximation to that you can be with local operations. So that is a limit. In quantum field theory, there's no limit. It's infinite dimensional, and Alice can put a lot of energy by just concentrating his action on a point. In fact, diverges for one point. So it depends on the dimension of your Hilbert space and the spectrum of your Hamiltonian, if you want. Yeah.
So I have a question about this scaling of the region where you're leaving the imprint from the negative energy. So it seems that at some point the field will vary on a scale which is very small, and then this dipole approximation that you are using is not vary anymore.
Right, that's true. In principle, yes. In principle, yes. So where we are, in here we consider only spatial distributions that are much larger than the size of the smearing that we're considering. But indeed, if you keep scaling, maybe atoms. So the macroscopic way of scaling is increase the intensity by the density of atoms and concentrate the atoms in a shorter place. But yes, of course, at some point, I mean, you're going to have problems of a high density of atoms too, and then dipole approximations are going to be fulfilled for sure. Yeah. But then again, that doesn't mean it cannot be done. This is just a simplification of the Hamiltonian to the interaction. In principle, the fundamental ingredients that you need is non-commuting with the free Hamiltonian and ground state having max rank entanglement. Other couplings, you may need to change the protocol if you have higher multiples contributing, but in principle could be done. There's nothing in principle that I would say stops it. Yeah.
I wonder if you can apply your ideas of entanglement eating, let's say, to the firewall scenario in black hole paradox. It looks like it's,
yeah.
Because, the firewall.
Yeah.
They say it's produced by breaking of entanglement.
Okay, yeah.
So it's something very close related.
It is indeed. Yeah, people have. I mean, I had a paper with Jorma Loco actually analyzing what happens. So in what we call the Rindler firewall. So toy model again. Rindler firewall is 1 plus 1D, and where we have a scalar field, and we break the correlations between the right wedge and the left wedge. We prepare the state that has the correlations broken. So that state is stress energy density singular indeed in the firewall, in the boundary of the firewall, but then we proved that particle detectors going through would not get burnt. That's a very interesting result. So sure, stress energy densities are infinite, but matter does not couple to the stress energy density of fields. Matter couples to amplitudes of fields. And it's not true to begin with. Two entangled detectors. So Jorma proved himself that the detector doesn't get burnt going through one of those Rindler firewalls. But what we proved together is that if the detector has entanglement, two detectors, one outside of the firewall, one's in a trajectory of falling into the firewall, they start entangled, the entanglement survives. So the firewall does not break further correlations. And Masahiro Hota has worked a lot into shooting this negative energy wave packets into black holes and doing siphoning energy that would come from the surface of the black hole connected to firewall models, and he's actually modeling using discrete models as everyone does though for what's going on the surface, because infinite dimension is not possible, we don't know how to do it, and he's getting interesting results. In fact, he's getting violations of the page curve hypothesis. So the typicality assumptions that are made about the Hamiltonians may not be as general as were originally posed. So answer your question, yes indeed, this is definitely connected with entanglement and breakdown of entanglement in space-time, and the firewall hypothesis, or firewall paradox, as some people call it. I don't know.
And there's a question. Can you generate a wormhole with this? Or?
So the next, okay. So the real claim is, in principle, you can maximally violate energy density. So the inequalities that limit the amount of negative energy that you can do. Now, can you generate a stable wormhole? So first, question number one is it legit to feed Einstein equations with the expectation of the stress energy density? There's a lot of work on that. So Ford, for example, has worked on this. And the conclusion was only if the state of the field is a coherent state. If it's a coherent state, then yeah, the fluctuations are under control. And then you can, it's okay to feed stress energy, Einstein equation with the expectation of stress energy density. The state that we have here is the state of the field is a cat state. It's a superposition of two coherent states of opposite phases. That's the state that you generate. And in terms of uncertainty, it's very close to coherent states. So this is kind of, it may be arguable if it's one of those states that is legit to feed in Einstein equations with that. In any case, you can do stochastic gravity with it, which is feed Einstein equations with the expectation of the stress energy density and feed the fluctuations of Einstein equations with the fluctuations of the stress energy density and see what happens. Classically, I'm not talking quantum, no back reaction yet, so stability is a different, but you can do that in principle. And that's something we're slowly doing because numerical relativity is tough.
So what happens with the fluctuations here? I mean, are they larger than the...
They are larger than a coherent state, but not much. It's a cat state kind of thing. And it's very similar. So in terms of the phase space, there's a cat state that is very close to each other. So it's kind of a push down, makes the vacuum, which is a distribution that is isotropic in phase space, makes it a little bit oblate, like doing a displacement like this, two displacements if you want. It's a probabilistic, it's a controlled displacement. Basically, that's you think of it gate-wise, it's a controlled displacement based on the outcome of the measurement, what you're doing. So the final state of the field, which is a controlled displace, is like in phase space, the distribution goes a little bit like that. Still close enough to a coherent state, we think, so that it's okay to feed Einstein equations with the expectation value. And in any case, we can always compute the fluctuations and see. But there's another thing. Now, if you actually, at time zero, have the distribution, and then a wormhole starts forming, then people have studied how stable those wormholes are when they're generated by distributions that violate those inequalities maximally, and that puts limits on the kind of wormhole. So has to be very small wormhole, and maybe it even decays because of Hawking radiation kind of fluctuations, so the wormhole is unstable when you have quantum fields in it. That's something that can be discussed, and something I'm looking into as well with Luis in the context of warp drives, for example, and Jose, who's here. And Carlos Barceló as well, who's not here.
Because you have the chronology protection conjecture and these things, no? In a sense, so.
Yeah, well, basically, if you do a quantum field theory in a background of a wormhole or a warp drive, then you get energy accumulations and fluctuations that get catastrophic soon.
They can diverge.
That's right. So there's a time scale that it takes for it to be catastrophic, and is related to how fast can you set up the wormhole, how useful it is, how big. Maybe you're not interested in a wormhole that is spaceship size. Maybe you just want a wormhole wire, which is 1 Fermi, like a nuclear atom, enough to send signals through. Maybe that's all you want. Then maybe. So there are time scales and limits that one has to do. In any case, what that means is within quantum theory, within scalar fields, this protocol violates maximally as much as you can do in terms of scaling.
Not very promising, is it?
Say again?
It's not very promising.
So that you're advancing Jose's result?
No.
Oh, okay.
No, that's the only possibility, actually.
Yeah.
It does overwork.
Yeah. We have several ideas to try to stabilize them. We've tried ideas that we thought were cool, and they will work for sure, but then they didn't.
Yeah.
General relativity is like that. But then there's a final one that I'm excited about that maybe we can talk about.
But just for fun, I mean, if you feed that equation with this kind, I mean, in the region that you have this negative energy density, you get a wormhole or something like that?
You can get a warp drive. That I can tell you. A small warp drive. A wormhole, I'm not sure. But it's got the right shape if you want to generate a wormhole if you want. Again, I don't want to superclaim here because they overclaim. The thing is that
No, just for fun. I mean,
yeah, just for fun, yes. In principle, yes. As like, is that the kind of distribution that, if stable, would generate a wormhole? Then yes. Yeah.
Have you discussed this protocol with experimentalists or not? I mean,
not much, but they would say, oh yeah, in principle, the couplings can be done for sure. But
this instantaneous coupling looks...
You can do it with Gaussian couplings as well, and make the Gaussian coupling like very fast, and you get this as an approximation. And what we can do, we cannot solve non-perturbatively for an arbitrary switching, in infinite dimensions. In finite dimensions, you can for sure. That may be a thing to look at. In infinite but countable, I mean in a cavity. But what you can do is do it, check with a Gaussian and estimate the error that you're making depending on the timescales. That you can do. We haven't done, but you can actually do. If someone gives me a timescale that they can couple, then we can work on estimating the error that the protocol would commit. So.
I would expect this effect to be ridiculously tiny. Right?
Yeah. As much, there are fundamental limits.
I don't think it should be.
Well, there are fundamental limits that come from how much can you concentrate the atoms, keeping the whole thing working as atoms.
You know, these things begin to be relevant when you have like a 400 times the mass of the sun in terms of and that, so.
Depending on the speed that you want.
Yeah.
Again, if you want a warp drive.
I don't think.
No, if you want a superluminal warp drive, for sure. But a subluminal warp drive is stable to begin with. A subluminal, if I want a warp drive that goes at 50 kilometers per hour, and you may, why do you want one? That's fundamental proof, right?
Subluminal is too easy.
It's kind of cool because in a warp bubble, if you're in the center, to all effects, you don't feel inertia forces. That's the kind of thing. And your proper time is the same as the proper time of someone at infinity. That's the difference. If you want to travel with a warp drive at, say, a tenth of the speed of light, you don't have the inconvenient time dilation problem that you're going to get people get old. With a warp drive, you are the same proper. Problems happen to the people you run over. The people that you run over, you mess with their time. But if you remain in the center and you pick a route there's no one, then it's fine for you and your family. They're still alive.
So in the protocol that you showed, you're assuming that both takes no time to read out the information.
Yes.
But why do you need that? I mean.
No, you don't.
No,
but the problem is that the amount of energy density and entanglement that you can access goes down. Carlos also knows that well. There's a decay on the amount of entanglement of the regions that you time-like and space-like decay. So if you weigh too much, you're not going to be able to optimally. You're going to get less. So the more you weigh, why you may wonder why do you actually do it at the time that the wave from Alice goes? You're going to have a lot of positive energy to overcome because Alice sends you a pulse. It's actually optimal. If you weight more, you can do negative energy, but less than what you would with Alice, because of correlations decaying with time.
And did you try the massive case?
No.
That doesn't travel at the speed.
But the correlations, indeed no. Correlations decay exponentially for a massive case. Yeah. No, it works, but the correlation would be ridiculous, so I expect it not to be better. Maybe a small mass would help, I don't know. But then again, not for what you want, right? So yeah, massive is something we're looking at. Also different couplings. One can consider fermionic fields, that's another thing we're looking at. The coupling to a fermionic field is quadratic on the field. You cannot couple to a fermion field. Fermion field is not to begin with, the operator is not self-adjoint. So you need to couple bosons to bosonic currents. So you make a bosonic current with the field. It's a quadratic coupling. Quadratic couplings tend to be better to take to push down and squeeze the entanglement in there. So maybe quadratic couplings are better. We're looking into that too, like the fermion kind of coupling. Fermion, one electron coupling to fermionic field, for example, something like that as a detector. Again, this is all for fun, though. Don't think that my claim is because we've been discussing with. No, I don't claim that you can do that in the lab. This is for fun. It's exploring the possibilities, if even in principle that's possible with this protocol. And how good is the protocol as compared to other people have proposed crazier protocols, such as an accelerated mirror to relativistic speeds. That is more crazy than this, I would argue, in terms of doing it.
So you are sort of exploiting in spirit the fact that you have a max rank entanglement. You can sort of do this energy extraction.
Mm-hmm.
What happens if you don't have quite max rank entanglement? Have you tried to see that?
For quantum energy teleportation?
You have a sort of n-dimensional in space and you have not quite max rank entanglement.
So, I don't know. And in fact, the theorem is only sufficient. So it's true. You may actually be able to do it with less than max rank entanglement. But it's guaranteed if you have it, yes. And in a quantum field, you have it. That's why we were focusing mostly on that. In the ground state of a quantum field, that's max rank entangled. That's why but then again, it's possible. So here, the key resource is definitely not entanglement. Necessary condition, max rank entanglement in the ground state, but you can do it even with states that are not entangled. Say a thermal state below T star that has no entanglement, it still works. It's mutual information somehow. It's correlations what you consume. You may argue there's this coordinate, if that plays any role, that is not known. But mutual information seems to be the resource that you're using somehow. Like zero mutual information definitely coincides with not being able to extract entanglement. sorry, my brain was going somewhere else. Doing QET. And again, QET is not just a field theory kind of thing. It's just this quantum info. It's a quantum info protocol. Only that in quantum info, people usually don't consider the energetics or the thermodynamics of it. They don't have Hamiltonians. They have 0 and 1. When they have Hamiltonians, but they don't count energy. When the usual teleportation, someone argued once, but this QET is worse than usual teleportation, because usual teleportation, you have the 0 state here, I have the 1 here, and I send you the 1 here. A lot of energy in the 1 here. It's like, no, but you're not factoring in that the operations that you do cost you energy. You need to keep track of all the operations you do, and you're not going to get energy out of that. And in fact, that can be shown that. So it's quantum information counting the energetics.
Okay. More questions? All right, so let's thank Ken.
Thank you. All right.